So, TensorFlow. We've learned what a neural network is, and we've seen how to write one in matrix notation. We've built one in NumPy, and that kind of completes our theory overview. So now we come to TensorFlow. What is TensorFlow? TensorFlow helps us build neural networks and perform some other sort of tensor-y computations, right? It's a fair point that TensorFlow is kind of a general framework for doing tensor-style operations, linear algebra-style operations, and optionally deploying them to the GPU, and it can be used for a lot of stuff other than neural networks, right? Although neural networks is certainly what we're interested in now. So it allows us to express a computation and then run that computation on data, right? The computations can be compiled and dispatched to a CPU or GPU, but the GPU dispatch requires hardware and software. Is irritating, requires specific hardware and software support, sort of above and beyond just getting TensorFlow working, and it's annoying enough that we're not going to worry about it right now, all right? By the way, what is a tensor? So a tensor is a generalization of matrices and vectors, okay? So both of matrices and vectors are tensors, right? If sort of a matrix is a 2D construct and a vector is a 1D construct, a tensor is an n-dimensional construct, right? Where n is any number between like 0 and, you know, any large, not infinity, right? Because it has to be finite, right? But 0 and any large finite number, okay? Alternatively, a tensor is how a mathematician pronounces n-dimensional array, okay? So a tensor could be a 3D array, or a 4D array, or a 2D array like a matrix, or a 1D array, right? In TensorFlow 1, so hence the name TensorFlow, right? Because we're manipulating all of these 1, 2, 3-dimensional regular data structures. So in TensorFlow 1, you would create a graph of a computation. All right? So you would write code that looked kind of like the stuff we wrote with NumPy. You would write, for example, w at x for matrix multiplication. Right? That would result in a graph of those operations. So instead of returning to you a NumPy array of your result, it would return to you a node in a graph that represented that computation, okay? And you would build these up because you could feed these nodes in to more operations, right? And build up incrementally this bigger graph. You would then create a session and you would evaluate whichever one of those nodes you wanted, optionally feeding some data, right? So this splits what we were doing in NumPy into two steps, right? First, you define your graph, then you create your session, then you evaluate your graph on data, okay? And this actually works fairly well. It's just sort of complicated and involved and a little bit difficult to learn, right? So TensorFlow 2, the big deal is that they switched to immediate mode. Immediate mode works more like the NumPy stuff works. In immediate mode, if you type something like this, right, you are going to get a tensor that represents the result of that operation, right? Immediately, without having to start a session, without having to evaluate it given some special input, okay? One of the other big changes they made, though, which kind of, in some ways, eclipses the first one, is that they moved to a high-level API first, right? And that's called Keras. By high level, I mean that Keras works in terms of models and layers so that you don't have to explicitly write this kind of math anymore. Okay? So the two changes in TensorFlow 2 are moving to immediate mode, so that when you type stuff, you get a result immediately, and then sort of putting the Keras high-level layers and models first, right? That's the preferred interface. All right, so a quick note here. Why even talk about TF1? Well, because there's a lot of material out there about TF1, right? So, if you are Googling about a TensorFlow question and you see code that is using a tensorflow.session, for example, that is TF1 code. That is either TF1 code or that's code that is using the TF compat model, but in either case, ignore it, right? You don't want code that's going to use tf.session, right? And yeah. That is old. That is like an old, outdated tutorial. Okay. So I mentioned Keras. What is Keras? Keras is a framework for easily building neural networks. We are going to be interacting heavily with Keras. To use Keras, you describe your network using high-level classes that Keras provides. Again, like model and layer and activation. And then Keras uses a back-end, like TensorFlow, to actually create and run the network, okay? Keras is, or was, independent from TensorFlow 2, right? Keras used to have a whole bunch of different backends. It could use TensorFlow. It could use, what's the other one? I'm blanking on the name of the one that died. It doesn't matter, right? Keras used to have multiple backends. Now it's a component of TensorFlow. So there are a whole bunch of examples, or a bunch of advantages of TensorFlow, right? So one major advantage of using Keras from inside TF2, TensorFlow 2, is that it is much, much easier than writing like NumPy code by hand, right? If we use Keras to describe our network in terms of layers and models and activations, right, Keras will then figure out all of the other details, okay? So Keras will automatically perform gradients, it will automatically figure out what all the sizes of our matrices have to be, and it will do all of that for us, right? It even has like automatic initializers for all of like the weight matrices, right, that are reasonable. So some of its automatic behaviors are reasonable in general, but you may have a reason to override them. We will not worry about that for right now. Another advantage is that it's ridiculously fast, right? So, like NumPy, TensorFlow and Keras get compiled to local CPU or GPU operations. That means they're going to be relatively fast, right? In my testing, right, in my experience, TensorFlow is intelligently multi-threaded, which means that if you have a multi-core, even running on CPU, it is automatically going to distribute across all of your cores, and you're still going to see a dramatic speed up, right? The fact that your Keras and TensorFlow code is going to be compiled to relatively efficient native code and then run multi-threaded without you having to do any extra work is a huge advantage, right? The fact that if you can get CUDA working, you can even deploy to the GPU, right, transparently, that's an insane advantage, right? And you can do all of this from inside the Python language, right? Where Python is sort of a much easier language to work with than, for example, Fortran. This is great, right? Because now we are Python easy while also being multi-threaded C fast, which is great. Another huge advantage is autograd. So by autograd, we mean the fact that TensorFlow and Keras will automatically differentiate our models for us, right? So all of that annoying calculus where we're trying to figure out d of d, like derivative with respect to a weight of the loss, TensorFlow and Keras will do that for us. So this saves us some drudgery, and it spares us having to do math that is easy to get wrong, right? And in some cases can be tricky, right? When we talk later about the cross entropy, the derivative of that thing involves the Jacobian. We don't need to worry about the Jacobian, right? Forget the Jacobian. Because Keras and TensorFlow will automatically figure out the gradient of that, right? Without us having to do any work, right? And that's very nice. That's especially nice if you're maybe not super great at multivariable calculus to begin with. Again, GPUs. Another huge advantage of TensorFlow is, under ideal circumstances, it can transparently deploy to the GPU, or, if you're Google, a tensor processing unit. And it does that without us ever having to write an OpenCL or CUDA compute unit ourselves, right? There have been people in my work group that did know OpenCL and did write a bunch of OpenCL compute units. It's not impossible. It's definitely a lot more work than expressing a model in TensorFlow is going to be, right? And it requires a very low-level model of the hardware that TensorFlow and Keras definitely do not. There is a downside to this, though, and it's that it requires you to get either CUDA or ROCm set up, and that can be kind of tricky, all right? Does the next slide go into this? Okay. So CUDA is the old NVIDIA one that's been around forever. NVIDIA has not had competition for a long time, and that means that they have maybe, I think I can say, not had to make this interface as nice as they might have wanted to. Well, okay, more concretely, NVIDIA very frequently snubs, like, ideal software distribution practices, right? So there can be some ugly parts about getting CUDA to work. ROCm, well, and one of the other problems is that CUDA only works with NVIDIA cards, right? One of the other problems is that CUDA has this kind of complicated support mapping where every version of CUDA is only supported by a specific version of TensorFlow, right? TensorFlow only supports some versions of CUDA, but each version of CUDA only supports some hardware, and so it can be a slightly irritating dance to figure out what the latest version of TensorFlow that you can use on your hardware is, and keeping CUDA and TensorFlow updated in step. So ROCm is the AMD one, right? ROCm is AMD's, I should say what CUDA does, actually. I just threw that out there and then didn't explain it. CUDA is a GPU programming library. That's what it is. That's NVIDIA's toolkit for programming their GPUs and only their GPUs. And I think it also includes, I think CUDNN is a part of that, which is a library full of optimized deep neural networks. So ROCm is AMD's analogous thing. It is the AMD proprietary library for only programming AMD cards. ROCm is much newer. AMD sort of waited a long time to see if somebody would do a hardware agnostic like OpenCL backend, and that never happened. And they basically finally decided, all right, we want data centers to buy our graphics cards, and that's not going to happen unless we do like something like CUDA and CUDNN, and that's ROCm. So the problem is, ROCm is much newer. ROCm is also irritating to install. ROCm is also unstable. I keep writing ROCm, right? And when I say unstable, I mean kernel crash unstable, right? Machine hard lock, like hardware reboot unstable. So this is a little bit irritating, right? GPUs are a big advantage. We are not... So it is on you, I should say. I am not going to require or support experimenting with GPUs for this class. If you want to try to get CUDA set up or ROCm set up on your hardware to do GPU accelerated training, more power to you. That's going to be your lookout. All right. So another kind of advantage, is optimization. I mentioned CUDNN, right? So CUDNN is that library. Ooh, what letter was that? Library of optimized implementations of networks, right? So under ideal circumstances, TensorFlow, if it can, will reach into CUDNN and use a very optimized version of a network, right? So CUDNN, for example, contains an implementation of the LSTM. That implementation is really fast and very optimized for NVIDIA hardware, right? So if we set up LSTM cells in our Keras network, if everything goes perfectly, we'll end up using the highly tuned LSTM from CUDNN, which is nice. Again, we're getting a bunch of speed transparently for free. All right, so before I go into downsides, let's have a video break.